So setting objectives for sorting projects, financial and technical aspects. We did that on purpose. That is a vague, anything goes kind of title, because in the end, we had a lot of trouble scaling down what we wanted to talk about, because there is a lot to talk about. Allow me to introduce my co-speakers. You have Lina from Primero, Process Engineer at Primero, and Jordan Zampeni, Senior Process Engineer at DRA, and myself, Ryan Cunningham, Process Director at CIMA. And to be honest, this all started from the fact that we have all been co-workers at DRA Montreal, and we are reunited for the greater good and our passion for sorting. Special shout out to Ned Hambling from Primero, who helped on a lot of the arrangement work that you'll see later on presented by Lina. And as a side note, like honestly, in the end of this, talk to any of us if you have questions. We will talk probably more than you were expecting about the subject because we are quite excited about it. All right, ore sorting. I would call it a champion of pre-concentration. And pre-concentration is this new thing that everyone's talking about. In reality, it's actually an old thing. It's just that we've rediscovered it. And it's becoming a lot more popular, which we will get into the why of. Ore sorting tends to go within the size range of 250 millimeters, depending on your material, depending on your densities. That's a rough size limit, 200, 150, depends, and down to 20 millimeters, but it's not limited to. It just becomes the lower effective range of you don't really want to go further than. But in food sorting and stuff like that, it goes all the way down to rice-sized particles. So what does that mean in terms of, like, why is this, honestly, pre-concentration is generally a shift in your perspective on liberation. Right now, most designs are based on liberation of your target mineral. You're looking at your target mineral and you're like, what is that size in which I actually get a separation of characteristics between my valuable particles and my non-valuable particles? Which means, because we've mined all the good stuff, we're looking at the micron-sized material now. Or the material that's in, places hard to reach, which drives up the cost of our projects. And this is why our CapEx keeps on going up and up and up per ton. What pre-concentration is now you're taking a step back. My material won't be liberated from whichever minerals or mineral it's associated with. What's the junk liberate at? What's the other stuff that I'm not paying attention to liberate at? And the thing is, that goes into, and like I said, I'm going to be, Jillian brought up the right references. The trade-off is really in the geology. It's really in how you look at your mineralogy, how you look at your actual material. Sometimes it's like, hey, let's take a step back and look at the entire ore in how it's, like the resource and how it's located in the ground. So here's an example of, pre-concentration. This is these veins are liberated at fairly large size. They use DMS to concentrate out, while the sulfides are these thin veins. You're trying to get a good cut of your waste material. And on that note, so the whole thing is now you're bringing a whole suite of properties in which you can use for your sorting. You're bringing the whole electromagnetic spectrum as, to help you. And the thing is, really, they can be pretty much classified into the surface ones, the ones where you look at some sort of the surface property and that's what you see. And then you got the transmission ones, which is like where you get the XRT being the best example, where you get the whole, what is the whole particle. All right, sorting efficiency. So there's two parts of sorting efficiency. The first is actually 100% about your sensor technology. Now this is the definitions are from King, from a paper, but essentially it comes down to, first, identification. Have you identified your target mineral properly or not properly? Have you targeted or identified your waste particle properly, not properly? Pretty straightforward. Now, something to be said for mineralogy when you come to a surface determination. This is when you look at a surface, when it's completely liberated, no problem, and when it's uniformly disseminated or uniformly mixed, no problem. It's when you have these particles that are half-half, because that's when you get the most error. When you can't see the backside of your particle, you might get it wrong, or it might not be properly classified. So that's when you're using surface-based identification. While transmission tends to give you a little bit of a better reading, but yet again, if anyone's ever done any processing with silicates, you realize that what is a proper silicate mineral versus a non-proper silicate mineral, sometimes it's a little bit of a soup. Silicates can have all kinds of impurities, spodumene being a pretty good example. Now, accepts, rejects, and deflect. The term is, what you're accepting and rejecting is a matter of perspective. What you might be trying to reject your waste material or your valuable mineral. Usually you're trying to reject or using the air to deflect the lower tonnage stream, generally speaking. But yet again, as we're going to get into, that may not necessarily be the right strategy for you. Because in the end, the second part of sorting efficiency is whether or not you properly deflect your material. Are you deflecting, you've identified your material you want to deflect, are you properly deflecting it? Then it gets into the materials that you didn't want to deflect that you're deflecting. Or there's the material that you wanted to deflect that you didn't properly deflect. In reality, it's actually the material that you did not want to deflect that you end up deflecting the most. And it comes down to this, your air is the most effective sorting medium that we have because it has quick release in terms of mechanically. So with a quick puff, you blow your material to where you want to. But the thing is, there's a pre-period where it's building up, and then you got your full-on period, and then you got your build-down period. And the thing is, it's not a perfect mechanism. A puff isn't a straight line either. So you're trying to use a cone to deflect material in the proper way. So it's not 100% accurate. And the thing is, sometimes we're spacing out the particles, but sometimes particles are on top of each other, even when you space them out. So usually what happens is you identify your target mineral, and it ends up getting ejected, and it carries some stuff with it. Sometimes it's stuff you wanted to go with it, and sometimes it's not. And then here's the example. This is ore sorting of lithium. So right there you have two trends. You have the orange, which is XRT. That is, and the best way to see that is you have properly identified it. There is less chance of wrong identification of your particle. But as you see, as you have more mass ejection, and in this case we are ejecting our lithium, you end up having a loss in recovery because you're carrying more junk with it. You're carrying along. Actually, sorry, I apologize. We're actually ejecting the waste. So what's happening is as you're ejecting more waste, you have missorting of your actual lithium, because as you're having more and more waste being sorted, you have lithium being misclassified. And then the next one is, the next lower line is the visibles, or the ones where you're using lasers, or the ones where you're using color, or those are the surface ones. So you can see there that there's a differentiation of that line to a lower efficiency because sometimes it's identified as waste on the top, but there might be a whole bunch of lithium on the bottom. So you can see both of those trends in the actual recovery curves. And the purpose of this is just proper appreciation for your material. It helps you contextualize. This is where bulk sorting would come in. If I can actually bring down or concentrate up the amount of material that I need to sort or not sort, this trend becomes an efficiency factor because I'm having less ejections, or what I'm ejecting becomes more targeted. So the thing is, upgrading or downgrading can actually have impact on the overall recovery of your circuit. Now on that note, so as an example, here's Thornaway and what they did, and they were trying to concentrate the kimberlite, and you can see there that they actually had, in their ejects, there was some kimberlite that got misclassified. They were ejecting out the waste. From there, they did another scavenger step, and then by doing that, they were able to get a full or almost a complete recovery of the kimberlite because that's what they wanted. And you can see there the final example pile of the small amount of kimberlite next to the actual waste that was ejected. Now I'm going to hand off to Jordan, who's going to get into more of the mechanical and the sizing considerations of the ore sorter.
Thank you, Ryan. You all hear me well? Yeah. So I'm going to look into, so first question is, when you want to introduce an ore sorter into your project, is your ore actually amenable to the ore sorting? And the amenability of ore to ore sorting depends on two major factors. One is the intrinsic heterogeneity of your ore, so what's actually in the ground, and the actual efficiency of your ore sorting operation. So how efficiently can you actually identify and extract those particles? And this one here is based on mineralogy, and this one is tied to equipment. So looking at intrinsic heterogeneity, if you look at Guy's sampling theory, you can evaluate a constitutional heterogeneity following this formula here, which is CH equals, anyway, all that stuff where the, I'm not going to read it out to you, but where NF is the number of all the samples, AI is the grade of each particle that you have, A bar is the average grade of your particles, MI is the individual mass of each particle, and then M is your total mass. And that allows you to generate curves where basically a straight line down the middle where X equals Y for mass pull versus recovery is your ore is homogeneous throughout the deposit. And moving up towards the top corner, you get more and more heterogeneous, which makes your ore fundamentally more preferable to ore sorting. You can get a better cut out of it. And this comes from a paper that's sourced there. So yeah, large CH values indicate high amenability, and lower ones indicate low amenability. Once you have an idea of whether you're heterogeneous or not, it's a good idea to look into whether it's worth sorting. So as Harold spoke about this morning, there's a lot of lab testing that you can do to confirm the ore sorting performance. So you run some rocks through some sorters, you get a signal out of your sorter, and that allows you to generate an algorithm which tries to predict the contents of these rocks. So how is the rock actually seen by the sorter? And that will allow you to make a decision whether you want to accept this rock or reject it. The accepted obviously being what you're sending to downstream processing, and the rejected being the waste. And as Ryan had mentioned, whichever rock has the smaller mass proportion would be the one you're actually ejecting with the air. And so looking at your heterogeneity of your ore, if you had a perfect sort where every rock you analyzed with the sorter measured the exact grade of that ore, you would have it sorted as such. But then actually if your signal is not quite in tune with what the actual grade of your ore is, you'll get a curve that kind of looks like this, where you have your rocks that are sorted from left to right based on signal, but your actual grade varies quite a bit throughout it. So putting that together, you can, at an early stage in a project, take this data and generate a mass recovery curve to kind of see how your project would perform integrating an ore sorter into your project. So let's say you have this curve here where I have an algorithm that did a not great job sorting my ore. Going from left to right, that's the order of the rocks sorted by signal. And then we have a cumulative grade curve for, let's say you take the first 20%, you go to the 20% point on that curve, and you can see what the grade of your recovered stream would be. And then with that, you have a grade recovery curve that you could slide along depending on how much you want to accept to your accept stream. And basically that follows the heterogeneity curve that we saw earlier, where a good curve is pulled up to the top corner, and a bad curve is pretty much there's no variation in your ore body. And so this can be used in an early stage of a project. You take this mass recovery curve, you plug it into a preliminary economic model, and try to get a good idea, yes, no, maybe, is this a good idea for a project? So with that, you can generate a high-level economic model. If you have a scoping study or a desktop study that's already been performed for a project, you can extract some data from it and add some assumptions for ore sorting and kind of generate a curve that says, okay, for various extracted or accepted masses, what kind of project benefit would I have? This is just an example where there was a fixed mill size with a variable mining rate. So let's say you had 10% ejection, you'd be mining 110% of your base case. So we had capital and operating costs added for the ore sorting plant that varied with the tonnage. So because you have a fixed tonnage per ore sorter, there'll be, let's say, 1, then 2, then 3. So the capital cost will increase in steps. And we can talk about the sizing of the ore sorters in the next slide. And then we calculated an NPV curve for every mass pull. And then you can see in this example that about 35% would be your optimum economically for this project to use an ore sorter, but you're still ending up rejecting quite a bit of mass. So going into the actual sizing of the machines, so as it was previously mentioned, the maximum capacity is dictated by a monolayer, and your maximum monolayer would be closed packed spheres on a belt, but that's not necessarily viable because you don't want your ejected air puffs to interact with any particles around the rock that you want to eject. So what you can see here on this graph is for various belt occupancies, which is the percent area of the belt that is covered by rocks as they pass through the sorter, what kind of theoretical tonnages you can get on a machine. And this is assuming a certain belt speed, a certain belt width, a certain rock density. So 10 to 20% is achievable in practice, and you can see that there's a linear relationship, and that's fundamentally because there's a relationship between the cross-sectional area of a particle and its volume, which is linearly related to its diameter. So talking about that 10 to 15, the 15 to 20% occupancy, there's actually an interesting paper that was run where it was kind of looking at the effect of occupancy and the impact of misplaced particles. And so what you can see in this picture here is there was Coopers who used 2 different types of plastic that he ran through an ore sorter, and with varying percent of each plastic. And he ran it at various occupancies through the ore sorter, going from like 10-ish% occupancy all the way down to 300. So that's, you have 3 stacks of material and you're trying to extract the particles that you want. And in fact, you could see that his recovery curves, just based on the mechanical properties of the machine, showed that above 25% you have pretty good recoveries. Below 25% you have pretty good recoveries, and so that 15 to 20% is a pretty good sweet spot. So in practice, I've seen this in literature where the curve, the sizing curve of your machine actually curves up a little bit, and I had interpreted that from at larger rocks you can have larger belt speeds or increased occupancies, but Harold also showed this morning a linear trend. So I'm wondering if for TOMRA's machines, if that's recommended or suggested to have that linear curve, or if this one from Will's is more accurate. But in general, the formula for calculating the throughput is belt speed times belt width times occupancy, which gives you a meter squared per second passing through, and then you multiply it by the ratio of your volume and your cross-sectional area times your specific gravity, and then a factor to adjust for time. And so you can calculate your throughput as such. And as previously mentioned as well, you can't really pick a specific point on that curve. You need to use your average particle size, which is a 3-to-1 ratio as a general rule. And that's typically because your air nozzles for one size are not going to be the same for another size, so you might not be able to kick out your particles with a different size. How am I doing on time? Okay. And so one major cost consideration is the air consumption, and that's pretty much the main operating cost for ore sorters. Ballantine and et al. Had a paper where they talked about the relationship between motor power for a compressor and its flow rates and pressures, and was able to calculate a curve that kind of looks like this, where your particle size is on the x-axis and your specific power requirement is on the y-axis. And for a given nozzle size, you can see that as you increase or decrease your particle diameter, your air cost goes up exponentially. Now, what this curve doesn't really show is that as you go smaller particles, you may drop down to smaller nozzle sizes. So it may not increase as dramatically, but there's still a relative increase in air requirements as you go down. And I think what that speaks to is if you can sort at larger size without compromising liberation, it's probably a good idea. And just one quick case study to talk about the throughputs and occupancies. When we worked on Renard Mine's ore sorting plant, they had this arrangement with two size fraction, 2 stages, and the larger machines were able to sort 200 tons per hour versus 60 tons per hour for the smaller machines, and they were only kicking out a little bit of mass, and so the second stage machines were pretty low belt occupancy, and so they had pretty good machine efficiency for sorting. And with that, I will pass it on to my ex-colleague over here, Lina, to talk about a bit more flow sheet considerations and layout considerations. I don't know if you want to.
I'll take this. Hi, good morning. All right, so we've talked about ore from the ground, what we can do. We talked a little bit about theory, talked about a little about throughput. So let's take this opportunity and run through some flow sheets together and see really how that puts together. So what we have here is really a dry ore sorting, so XRT, and it's a single size fraction, belt type. So what we see here is we typically have a sizing string up in the front, and that is really to govern that top and bottom size ratio, to be able to respect that, give our ore sorter the best possible chance of reaching that recovery. So we'll kick out the fines. So this next step here, I think what we actually touched up a little bit in the seminar today is layout consideration. Why building out, building up? What's the difference? Well, here we decided to go with a conveyor. And the reason why is we want to build out. We don't want to bring that string up high. Having vibrating structure up high is not great, especially for CapEx. Structural cost a lot. So that is a consideration. But if we're in cold weather, for example, now we're looking to put buildings around everything. That building cost, especially now with COVID, it gets very expensive. So potentially at that case, or footprint limitation, we're looking at building up. And that's a trade-off. And next we know, once we transfer the ore into, sometimes we depending on where it sits on the flow sheet, if you have a certain amount of surge capacity, you can forego a surge capacity bin. But sometimes it's nice to be able to just smooth out that feed, to be able to respect that monolayer. And then we typically go with a vibrating feeder. And that is really to give us that feed control and for that feed presentation that Jordan and Ryan both talked about. Then of course, we have the main meal, the ore sorter. And this one here is it's an XRT. And like Jordan talked about, we need compressed air to eject particles. So that's the design consideration there, as well as, since this is a dry process, dust collection. That is something to consider. Ducting is expensive. And lastly, of course, materials handling. That's something that we sometimes forget about. When we talk about high-level study, is how we're going to be able to handle this, or where we're going to bring it to, how we're going to collect all these things. So I just ran through pretty quickly on a non-surface, an XRT. So what happens when we bring water into this? What happens if we have to wash? So now we're talking about, optical NIR or XRF, which is not often used, but it's still there. So what happens when we bring that water in? So there's a few things, and you can see in that picture, washing the ore really does make a difference. I mean, it's the same logic of why we wash our drill core, to see our mineralogy a little better. It gives that feed a little better presentation. But now we're bringing another layer of complexity into this process. So some things to consider. Effluent handling. How are we going to bring that water to the plant? We're talking about potentially, let's say, a crushing circuit. Well, how are we going to bring it there? How are we going to bring it back? And now if we bring our wet plant that we're sending a stream up front, how are we going to decouple that? As well as if we're in cold climate, what happens when you have dewater ore coming down and you're trying to store it? Does it freeze? So now it's a similar flow sheet what I showed before, now with a wash screen. So you'll see that there. So we're bringing water from a downstream flotation plant to wash the ore. So now we collect the water with a very traditional, pump box and a pump to be able to bring it back to that wet plant. But because we're doing that, like I said previously, so typical when we don't cross-contaminate effluent, we typically use something between a crushing plant and a wet plant. We use a fine ore storage to be able to break that availability a little bit, because I want to run my wet plant when my crushing plant is down, and vice versa. But now we have bring that effluent in. That's another layer of consideration. It's not impossible, just a consideration. And as well as, of course, we've all heard about bin freezing. It's a real struggle in northern climate. And what happens is, instead of you sending dry ore down that's frozen, now we're also sending water with our ore. So we've gone through a few simple ones. So this one looks very similar to what Jordan's presented in terms of storing away is, okay, I have a wide band of PSD. I need to sort in multiple size fractions. What does that look like there? As you can see, it gets a little more complicated. So let's say the top deck oversize, well, let's call that coarse ore. And that really looks the same, right? You're conveying to a screen, you have potentially a surge capacity, maybe, or a feed presentation, that's okay. But now we're talking about fine ore sorting. Because we're sorting a finer size, we're looking at a slight decrease in throughput per sorter. We might be looking at multiple sorters, how we're gonna divide that feed. And that's really the key there. And another one, we are now talking about more sorters, more outstreams, potentially effluent to handle. How we're gonna handle that, how we're gonna bring that in with less conveyor or less materials handling as possible. So now I'm gonna dive into just, we talked about a few flow sheets, how that kind of looks in space. But before I start, I just kind of wanna talk about layout is a living and breathing thing. It's complex, it's driven by a lot of factors. It can be done in many ways. What we're presenting here is really just a high-level sketch. There's always room for optimization. And of course, you guys are totally welcome, and we can have a full-on discussion about this. So here we have a single-stage belt-type ore sorter, and we're just gonna keep it simple. One ore sorter, keep it simple. So you can see that surge bin here. And you can see how that drives up that height of the conveyor. And this is why a lot of operations forgo that surge capacity. They'll say, you know what, I'll take the hit, potentially maybe I'll get a surge through my ore sorter that's a little too high, but I'll take it. And you can see that why. The next one, vibrating feeder. I'm not gonna go too much detail about that now. And materials handling. And you see how that tail pulley of these conveyors, they actually drive the layout, they drive the height as well. That's a consideration. So what happens if I wanna throw in another ore sorter? What does that look like? Second, so this is one way of doing it, using a pant leg chute or diverter chute to passively split mass. And you can see immediately our height went from H to 1.35 H. Obviously, these are just really high-level numbers there. And that's really to be able to kind of passively divide that mass coming off of the head pulley of the conveyor and to be able to divide it into bins. And here, we would definitely recommend a surge capacity, because for here, it's something that's passive. Rocks fall how they want to fall. We'll try our darnest to kind of control it, but it is nice to be able to just smooth out those feed to give that a little bit of control back. And you can see, so what's highlighted in blue was what we had at a single stage. It's getting a little bigger. So what happens if I have 3 ore sorters? What does that look like? Well, layout changes quite a bit. And that, again, is driven by the bin feed system. How we're gonna divide that feed through multiple bins. It could be 3, 4, 5. So one here we have showing is a shuttle conveyor. So what that is really just a conveyor with a head pulley that goes back and forth, distributes the feed across the bin. But you see how that, because of the take-up of the shuttle conveyor, actually pushes out that horizontal length of that conveyor. Effectively, that pushes our layout outwards. And if you have footprint, that's definitely a consideration as well. And then surge capacity. So typically we talk about surge capacity, you know, we talk about a couple minutes and it's really to smooth out that feed. And now we also have to consider it's really now also a function of a conveyor travel. I want to still be able to feed my ore while my shuttle conveyor is feeding other bins. I want to have that volume there. And finally, the discharge conveyor. And here's the fun part is we talk about discharge conveyors on the ground, but you'll see as we add something like this, and this is a simple arrangement where we have 3 ore sorter parallel, and we're trying to collect on one conveyor. But that pushes the horizontal portion of that conveyor out. So if you need to get up somewhere high, you might need to consider a little more length. Of course, there's things that we can do to steepen up that conveyor height, but that is something that happens when we add more and more ore sorters. Okay, so, and you can see here, that length really is, the more equipment that you add, that complexity drives up. And really that's kind of goes back to what Ryan was saying earlier in this, where ore sorter, the equipment itself, we're talking about ore sorter, it only counts for a small portion of it. And this is why, is because we have to have all these systems to support a structure like this. So I hope I gave you guys a little bit of perspective on what it looks like and how that complexity drives up and why we look and our engineering solution. So I'll pass it back to Ryan to wrap it up.
Thanks very much, Lina. So on that note, what we try to do is we try to at least give you a little bit of the ideas of, you know, beyond what's required for the sorter and what's required beyond of. Now on the notes of, you know, trade-off studies and how to properly set them up, I'll take the criticism from Jillian, like engineering companies, we are limited creatures. And one of our biggest limitations is data, and that gets the test work. And the thing is, so yes, it's 100% true, scale up is 1-to-1 with ore sorters, which is great. That's not the challenge actually in this particular test work scenario. It's getting the proper sample. If you want to test large rocks, you need large rocks. And the thing is, let's get it, how do you get large rocks? Do you drill those? Well, you could argue, oh, just take a surface blast. Here's the thing about surface samples. They have been weathered. What's weathering? Water, oxygen combine with your material and break apart your material. You're chemically changing that material, and usually that stuff is slimy. It's gritty, it falls apart. It's not, that's usually why most startups, people are like, oh, where'd all this stuff come from? Where'd all this slimes come from? That's weathering. So if you grab a weathered sample, that's not representative at all. So the thing is, you need a deep down sample of competent rock. So you're going to either need really big drill cores, which is expensive. So you see it's a bit of a back and forth. That's the catch. So that's actually the technical challenge we need to get innovative on and find solutions for. I'm all for, I think demo plants are delightful. Thing is, no one likes to pony up the money for them because they're expensive, and you know, people are like, oh, why, you know, isn't the test work enough? Well, you know, maybe not. The thing is, if you can start actually doing a little bit of a blast, a deeper blast, you can get the material that you actually need to test, right? So on that note, that's the challenge, I have to say. Now, yet again, what's the proper trade-off? Well, you have to start with what you have in the ground to repeat. You know, if you have a nice thin vein and you want to get everything at that contact zone, ore sorting is great. When you have a 1-0 type of material, because then you'll be able to mine that material without worrying about the waste of the dilution. And if you have multiple veins, even better. If that material interacts with your process, yet again, it goes back to testing. We're all guilty of this. We don't properly test the impacts of waste. We just say, oh, here's a representative sample. It's 10%, 5%, whatever. The amount of waste is mixed in if you've done it right. But the thing is, some waste is benign, it has no interaction, or it's actually preferential. It actually has a synergy. It actually sometimes shows up when we don't want it to show up. And if we don't understand that relationship, we can't properly balance the impacts that ore sorting will have on the economics. But here's a fundamental. Higher grades through your process result in higher recovery. And there's a very simple reason why. Anything below approximately 35 microns doesn't care about all the other physics. It only cares about water. Hydraulics are the dominant force. So wherever your water splits, anything that reports in that size range follows the water. So if you have a bunch of junk in that size range, guess what? It will preferentially follow your water to your concentrate and your tails, depending on your water split. So if you don't have anything in that, if you have less waste, you get better recovery grade relationship. That's it. You're always going to get it. So that's the process aspect. You can get into the grinding aspect. It was already mentioned. Usually our waste materials are harder and more abrasive, generally speaking. So there is a relationship there. Environmentally, guys, like that's the one we need to be pushing here, because the thing is, tailings handling of micron-sized material versus larger rocks is a huge savings, not just from a sustainability point of view, but also on a cost point of view. Because then you can just stick that into a truck, move it, and it becomes part of the material that you use to berm your tailings dam if you do it properly. So yet again, you have to take that into consideration. So all these things go into your actual trade-off, because if you don't grab these values and you just see the cost of the ore sorting with all its associated equipment, you might miss the opportunity. You might get the so what. It might not look attractive. Now, on that note, and the thing is, like I said, I'm so happy to talk about this later. But Erin's next, and she's delightful, so we should give her time. Is the fact that, combinations or smart flow sheets are required. Bulk sorting. If you actually pre-concentrate your material and change the mass split, you improve the recovery. And this is not new. This is actually really old. The drive to larger and larger and larger plants to help with the economics has made us simplify things. That's the mono focus on the liberation. That's the simple flow sheets. But if you go back just 50 years, the flow sheets did all this. They would look at smart ways of segregating the sweet material from the less sweet. That's where the innovation is required. Like, if you can actually campaign your contact zone material, or have a smaller plant just for that material and have selective blasting, you've reduced your capex. If you can actually, honestly, as long as you plan for an ore sorter, you don't have to build it again at the beginning. You build it when it makes sense in your actual mine plan, and you move your capital, and it helps your financials. There's a million and one considerations that you can do. If you don't design it in, it's going to be impossible to fit it in. But if you leave the space for it when you're conceiving it, you don't have to pay for it, but you have that option to execute once you build. So on that note, I'm just going to quickly, we do have a few pictures, but I'm going to move on. I'd like to thank everybody, and like I said, please hunt us down after. We'd be happy to continue the conversation.